Okay, so welcome everyone. So I'm Hannah, and today we've got another AI for Net Zero webinar series. So this webinar series is designed to bring together experts, innovators, and enthusiasts from both the artificial intelligence and sustainability domains. We have an overarching goal to accelerate progress towards net zero. And with this series, we aim to engage and inform communities about the groundbreaking research and developments at the intersection of AI and sustainability. So the series will delve into diverse applications of artificial intelligence across various domains crucial to achieving net zero objectives, including energy, transport, environment, agricultural, and food systems. So today we have a special guest speaker, Dr. Gege Wen, is an assistant professor at Imperial College London with a joint appointment in Earth Science and Engineering and Imperial AI. Her research focuses on developing computational methods for earth science and environmental science challenges to support society's energy needs and the transition to a low-carbon future. So Dr. Wen specializes in multi-phase flow and transport for CO2 geological storage, sustainable subsurface energy storage, and machine learning for scientific computing. She earned her PhD from the Energy Sciences and Engineering Department at Stanford. She's also the creator of the CCSNet.ai, an AI-based physics simulation tool for modeling geological CO2 storage. So welcome, Dr. Wen, and over to you.
Hi, everyone. Thank you very much for the introduction, Hannah. It's my pleasure to be here today to talk about my research on CO2 geological storage modeling with machine learning. And I hope the topic is interesting to the audience, to the webinar. So I want to start my presentation with this favorite figure of mine that describes how the subsurface is playing a very crucial role in the energy transition. On this image, we have a suite of energy generation technology on the top of the ground surface and different subsurface technology that go with these renewable energy generation technology. For example, we can combine natural gas power plant with CO2 geological storage and generate a stable base load energy from burning the natural gas and sequestering the CO2 in the subsurface formation. We also have geothermal in the subsurface. On the surface, we can have hydro, solar, onshore wind, and offshore wind. And when we integrate these wind and solar energy into the energy system, we also want to combine them with the storage technologies such as hydrogen storage, compressed air storage, brine storage in the subsurface. So I think with this figure, we can all get a good understanding of the fact that subsurface is not being used less as we are transitioning into a renewable-based energy system. Instead, the subsurface is only playing a more active role in the energy transition. So my research focuses on the geological storage of CO2. And this video is a really good description of how CO2 storage how CO2 storage is being done on a large scale when it's combined with a new energy system in the energy transition. So this example shows CO2 coming from a concentrated source and got arrived pipelined into a storage site. And at the storage sites, it was distributed into these 4 different injection wells. So as we're injecting the CO2 into the subsurface, because we're adding this volume into the subsurface, we naturally will add a pressure buildup into the subsurface formation. And it is very important for us to understand how much pressure we're adding to the subsurface, because the pressure that we're adding to the subsurface needs to be controlled so that we don't accidentally fracture any formation or cause any seismicity. And in some countries, the area where we add the pressure is also required when we apply for permits. And that defines the area of review where we need to understand the subsurface better to know whether there is any abandoned well in the region that will potentially lead to leakage. So it is very important for us to understand the pressure buildup. And in addition, we also need to understand how far our gas saturation plume has migrated in the subsurface. So after the CO2 is injected into the subsurface, we have a separate phase gas of CO2 in the supercritical phase that will quickly float to the top of the reservoir because of buoyancy. The supercritical CO2 is lighter than formation fluid. And as a float to the top of the reservoir, it also migrates laterally. So we need to know how far the CO2 plume has migrated to, and is that going near any potential faults or fracture in the system? Is that plume approaching a abandoned well? So these are the things that we need to understand very carefully when we design a CO2 storage project. So in order for us to understand this pressure buildup and gas saturation, the process that we are interested in is called the multi-phase flow process. So on the pore scale, the multi-phase flow is governed by Navier-Stokes. However, it is very, very challenging to resolve multi-phase flow on the pore scale. So in reality, when we simulate for the subsurface, we typically just do some averaging and simulate the reservoir scale subsurface using a multi-phase version of Darcy's law. However, although we are doing this averaging, numerical simulation is still very time consuming for CO2 storage. And that is because we need to couple our simulation with multiphysics, for example, thermodynamics, geomechanics, and reactive chemistry. And at the same time, we need to simulate the CO2 storage in a very, very large scale. And in addition to the large scale, we also need really high resolution. Like in the video I showed earlier, the pressure plume can very quickly travel hundreds of kilometers. But near the injection well, if we want a accurate simulation of the CO2 plume, we need simulation resolution of about 1 to 2 meter thick grid. So when we're comparing this hundreds of kilometers with this 1 to 2 meter grid cell, you can see why the simulation can take a very, very long time. And the last point that I want to mention is we also want to simulate the CO2 storage process for a very long time. For example, in Canada, sometimes the regulation requires the project developer to prepare simulation for hundreds of years after the injection have stopped. And that altogether creates a really hard problem for numerical simulation. And in addition to the multi-phase, multi-physics, and the multi-scale, we also have a inherent problem of the subsurface, which is the fact that geological distribution is always uncertain because we cannot see through the Earth. So because of this uncertainty, we need to do our forward simulation repetitively. And that also often requires either history matching, seismic inversion, optimization, UQ, or sequential decision making. And all of these requires over and over again simulate this really hard multi-phase, multi-physics, and multi-scale problem. So I hope by showing this slide, I can convince you that simulation is a challenging task for CO2 storage. And to tackle this challenge, we want to design, build, and train a machine learning model to provide a general purpose numerical simulator alternative. And the goal for doing this is to provide flow predictions that are significantly faster with high resolution and also comparable accuracy to simulation. And the next part of this presentation will discuss how we are going to approach these research goals. So to approach this problem, the first thing we did was we revisited the workflow for conventional forward simulation. And that typically includes 3 steps. Step 1, input. Step 2, numerical simulator. And step 3, output. For the input, we categorize general inputs into reservoir condition, geological model, rock properties, and injection design. And after passing a numerical simulator, we collect the output of pressure distribution, CO2 gas saturation, sweep efficiency, solubility trapping, and the mass balance. So these are the things that we typically get from a numerical simulator. So if we can sample our input ranges wide enough to cover the most realistic scenarios, and if we can design the output space to cover cover the general practical use cases of these simulation, can we train a machine learning model that people can use as an alternative to the numerical simulator to give us fast results? So this is how we think about the machine learning powered general purpose alternative. And we attempted 3 different type of architectures in approaching this general purpose alternative. And in the next part of this talk, I will go through each of these in detail. So the first architecture that we have used is convolutional neural network. And we applied the convolutional neural network into a 2D radially symmetrical reservoir. This is our initial problem setup, which mimics a flat salient formation and an infinite acting boundary. This is a really large box. The radius was 10,000 meters. And with this laterally infinite acting boundary reservoir, we exhaustively sample the input space according to these 4 different categories: injection scheme, reservoir condition, rock property, and geological model. And luckily, we have a good sense of a lot of these parameters. For example, for reservoir condition, we know the typical depths of CO2 storage project. We couldn't inject CO2 to anything that's shallower than 800 meters because the CO2 will be in gas phase. And when we're injecting too deep, the cost for the injection well is prohibitive. So we can design these parameter ranges according to this prior knowledge of the CO2 storage process. And after we have generated a large range of inputs that cover all of these spaces. We then run numerical simulator Eclipse. This is software by Schlumberger. It's well accepted by the industry. And for the output, we can collect the gas saturation, pressure buildup, molar fraction, and density of CO2 that's corresponding to these different combinations of the input. So because we were simulating in this 2D radially symmetrical reservoir, we can configure our input and output into 3D matrices that are X, Z, and the third dimension will be T. We can stack all of the time snapshot on the T dimension, and then we can get these 3D matrices. And using these 3D matrices, we designed a family of convolutional neural network architectures for CO2 storage problems, and we named this architecture CCSNet. The CCSNet contained 6 different models. We have 1 saturation model, 1 pressure model, 2 molar fraction model, and 2 density models. And the combination of all these models provides everything on the right-hand side, which are the typical outputs that we need for CO2 storage. So we trained a convolutional neural network, and we got excellent prediction accuracy. On this slide, I have 1 example in the test set. The first row is simulator prediction, simulator's output, and the second row is the machine learning prediction, and the third row is the absolute error. We can see that the errors are very, very small, and for the test set that are unseen during training, the average R-square score was 0.998 for 500 samples. And very similarly, we have high accuracy for pressure. The R-square score can be 0.996, and molar fractions and also densities are all, we can all achieve very high accuracy. And the best thing of doing this is that after we train this machine learning model suite, we get 10 to the power of 4 times speed up for the prediction. And to demonstrate this speed up, we designed a web application tool called CCSNet.ai. So this tool is free for everyone to use. Feel free to take a look and register. You just need an email and it's all free. And once you go on to CCSNet.ai, the website allows you to generate your permeability map, a random permeability map on the fly, and the model will instantly render the saturation on the bottom as we're showing here. And you can also get a prediction of the pressure buildup, the reservoir pressure, and it calculates the sweep efficiency factor for you. And in this example, you can also download the output. And in this example, I am changing the standard deviation of the permeability map from 15 to 35. So now we have a more heterogeneous reservoir. And with this more heterogeneous reservoir, first you see instantly the output gas saturation map, which traditionally would take hours to simulate. And you also get a automatically calculated sweep efficiency factor at the bottom. And this example actually shows the higher heterogeneity will give you a better sweep efficiency factor. So we are very excited, and this tool is being used by many users in the industry. And we're receiving about 1,000 requests per day from academia and industry together. But there was a catch. And the catch was that to train this model, it took us 20,000 sets of training data. The 20,000 sets of training data was marginally manageable for this 2D example. But as I mentioned, this example mimics a infinite acting boundary flat reservoir. And as we want to increase our problem complexity into 3D and more complex geological formations, the training data will no longer be manageable. So that is why after we have created the CCSNet, we then went on to a quest into finding a more efficient architecture for this problem that can also give us a good efficiency. And we met some brilliant computer scientists from Caltech and developed something along a direction called Fourier neural operator, FNO. So to compare convolutional neural network to Fourier neural operator, I want to use this example. This is a picture of my dog, and say my dog, his name is Doctor. Say Doctor is our input function. If we use convolutional neural network, we're sliding a convolutional kernel across every location of this image of Doctor. And at every location, the convolution operation is actually performing this convolution of function f convolute with kernel G. And here, the kernel G is always a local kernel. At each time, we can only see this one portion of the image. So this operation is inherently local. It is, yes, the point I'm trying to deliver here is that the kernels are local. And the difference from from FNO to CNN is lying on the fact that the FNO kernels are global. So take this original image of Doctor again. If we do a fast Fourier transform of the image, we can obtain this very chaotically looking image at the bottom. And each point on this chaotically looking FFT image represents a Fourier mode, and each Fourier mode represents the entire field. And something that's really nice about the fast Fourier transformed image is that the algorithm will automatically place all of the important Fourier mode coefficients on the four corners of this image. So because of this effect, we can actually use information compression to efficiently learn the kernel, the global kernel. So in this example, I am masking out the less important coefficients in the middle and retaining 16%, 4%, and 1% of the coefficients. And then we do an inverse Fourier transform, and we can obtain the recovered image of Doctor at the top row on the right-hand side. And we can see that even with only 4% of the coefficient, the image can still have a really good quality. And this is also the basis of a lot of information compression algorithms in nowadays world. You almost encounter this every single day when you watch YouTube video, listen to music online. And FNO architecture also uses this really great feature of information compression. So when we want to learn a kernel in the FNO architecture, we apply the kernel onto these filtered image. And because this Fourier kernel is learned in the Fourier domain, each point corresponds to the full field. Therefore, the Fourier kernel G's are always global. And another good thing about the Fourier transform is that convolutional operation in the Fourier domain is just a pointwise multiplication. So this is also very easy to implement in algorithms. So that is the main difference between CNN and FNO. And the takeaway message here is information compression is used to achieve efficient learning. And here summarize the different type of kernel. For CNN, we can have these little small kernels that shows different patterns in the image. And for FNO kernels, they are global. They are not very recognizable by human brain, but they covers the entire field. So taking the advantage of this architecture FNO, we propose a architecture called UFNO that's specialized for multi-phase flow. So UFNO, we did special tricks to improve the accuracy of the gas saturation with the shock front. And here is a comparison of the UFNO architecture compared to the convolutional neural network baseline. And you can see that the error is significantly lower for the UFNO across the entire simulation domain. And the best thing that we're getting from this architecture is the fact that we can save a lot of data. So in this figure, we're showing the performance of the CNs using the blue line and the performance of the UFNO using the red line. And with the same test set error, say the test set error of 3.4%, you can see that the convolutional neural network uses more than 4,500 training data, while the UFNO only uses a little bit more than 1,000. So we save a significant amount of training data when using this architecture. So with this data efficiency that we gain from developing this new architecture, we then have the confidence that we can go on and work with more complex reservoirs. So the next reservoir that we tried with was this basin scale 3D reservoir with multiple injection well. This is a really large domain. The X and Y's are more than 160 kilometers. And we're simulating a 100-meter thick layer. And also the reservoir is slanted. So given this reservoir size, this really large reservoir size, if we want to simulate with an optimal cell size of 20 meter by 20 meter by 2 meter, that will give us a problem dimension of 8,000 by 8,000 by 50. And if we times this together, it gives us a whopping 3.2 billion cells for the simulation. So it is virtually impossible to simulate this many cells in numerical simulation. And it is more impossible to generate a large data set that can cover a wide range of input using such a large grid cell number. So there's a huge gap between reservoir size and the required resolution. So to solve that problem, we applied a technique called local grid refinement, the abbreviation LGR. It is a popular approach to simulate the large-scale reservoir at different resolution. And we applied 4 levels of local grid refinement near each injection well. And after applying the 4 levels of local grid refinement, we can simulate the same reservoir size using the same finest resolution, but we can reduce 3,000 times of cells. So this makes the problem possible to be conquered, and we use this approach to generate a data set to train our model. And another thing that I want to mention here is you can see the LGRs is slightly shifted to the right hand side of the of the uh, of the uh, uh, of the square. And the reason of that is because we considered different slopes of the reservoir tilting in the dataset. So CO2 will naturally migrate to updip, and we reserved more space on the updip and always confine the gas saturation plume within the LGRs. We never simulate the gas saturation plume using the coarse global grid. So here is a example of such data with LGRs. So this is a 4-well case. You can see on the reservoir, the 4 wells are, we randomly selected locations to place these 4 different wells. And each well, because the reservoir is slanted, each well is placed at a different depth. And also each well has a different set of injection rate and also different set of injection perforation interval. And on the permeability, random permeability map, you can see the white line separates each local grid refinement area. And for the output on the bottom, we're showing the pressure buildup that's corresponding to this this input combination. And we simulated a time period of 30 years, and this is the last time snapshot. So now the challenge becomes, given this data set with multiple injection well, basin scale reservoir, and the special architecture, the special data architecture of these LGRs, how can we train a machine learning model that can predict the data with these LGRs? So to tackle this challenge, we introduce a architecture based on the Fourier neural operator architecture that I introduced earlier, and we designed something called the nested Fourier neural operator. So the nested Fourier neural operator contains 5 different models, and each model is corresponding to each level of resolution. Level 0 is the global level coarse grid to capture the global pressure interference between different wells. And as we go from level 1 to level 4, we gradually have more refined grid cells. And to make these models talk to each other, the way we did it is we feed each coarser level model's output into each finer level as input. And by doing that, we propagate the information of how the wells are influencing each other all the way down to level 4, which is the near well location. And after we connect these 5 models, we then take each model and output the prediction of the pressure buildup at the third time equals to 30 years. And we assemble all of these different pieces together for the 4 wells. And now we have a full field of pressure buildup across the entire domain. So this is the complete architecture of nested FNO. In addition to the 5 models I just described for pressure buildup, we also have 4 additional models for gas saturation. And the gas saturation models are responsible for predicting all of these complicated migration patterns in the reservoir. And to echo with a point that I mentioned earlier, we only have 4 levels of LGR models for saturation. We don't have a global model for saturation, and that's because we have carefully designed the data set so that the saturation is never being simulated with the coarse grid cells on the global level. We always have the gas saturation plume within the LGRs. And another point that I want to mention is near the injection well, you can even see these area of really high saturation. This is saturation of nearly 100%. This is an effect called dry out. It happens when the liquid phase in near the injection well is vaporized into the gas phase. So the water is in the gas phase. And the dryout effect is a complex physical response that only happens if we can simulate the reservoir with really high grid cells, high resolution grid cells, and we can capture this physics in the data set. So here is an example of the nested FNO's prediction. On the top row, we have the ground truth gas saturation by eclipse, and the second row, numerical simulator eclipse. And the second row, we have the predicted gas saturation, and this is for well 1, well 2, and well 3. And the average test set plume error is about 1.8% for unseen data. And similarly, we are satisfied with our pressure buildup, which has about 0.5% error in the test set. And as for the computational efficiency for the nested FNO, the prediction time is from 0.025 second to 0.085 second on a 100 GPU. And the numerical simulation runtime was from 2 to 16 hours per simulation. And that is paralleled on 20 high performance CPU on the Stanford cluster. So we cannot really do a apples to apple comparison because there was GPU inference and CPU inference. But we try to make this a fair comparison, but still we're getting a speed up of 400,000 to 700,000 times. So up to this point, we have talked about convolutional neural network and Fourier neural operator for CO2 geological storage modeling, and we are happy with the result that we're getting, and we think that is a good direction for training these machine learning models as a general purpose numerical simulator alternative. But there was another type of problem that none of the convolutional neural network or Fourier neural operator could handle, and that is the case when we are modeling reservoirs with faults. And this figure here shows why the faults couldn't be modeled very efficiently by CNN or FNO. So imagine we have a slanted fault line here. If we're using a regular mesh to represent the fault line, we're actually representing the fault line with the staircase shape, where if we want to model it more efficiently, we would want to align the grid cell with the fault line and give a better representation of the continuity of this fault line. So in industry, when people model faults, it is a common practice to use irregular mesh that aligns around the fault line. But convolutional neural network couldn't do that. So we introduced a new type of architecture called graph neural network. So I'm taking back the example of doctor's image from before. And if we're using a convolutional neural network or FNO, we are applying these lattice-based grid cells across the entire image. And the cells are all in a Cartesian domain. And we can see that each time when the convolutional kernel goes across this, it sees a regular square patch on this image. For graph neural network, if we have a input function like this, we can just discretize the domain into another type of discretization that is irregular, and we can still extract we can still extract the information of cells and which cell is next to this center cell. But instead of having these patches, we're representing things in node and edges. So the center cell will be a node, and it is connected to the cell next to the cell by an edge. So here I'm showing the fact that the CNN-based architecture is also a type of graph neural network by a special case where all of the node and edges are aligned perfectly on a Cartesian grid. So when we're training a convolutional neural network, when we apply the kernel onto this lattice grid, we are calculating element-wise multiplication, and then we sum it when we do the convolution, and then the result is our new feature map. And the graph neural network actually have a very similar structure, but instead of element-wise multiplication, we use something called a message computation. We take each node of interest, we go pass that through a mass computation neural network, typically a multi-layer perceptron, and then we do aggregation, and then we update the center node. So it's very similar to convolutional neural network, but it's more flexible and applied to different number of edges and different number of nodes across one center node. So with this new architecture, graph neural network, we applied this architecture to a 2D reservoir with impermeable fault lines. So on this example, we are showing 3 different type of meshes, where each mesh have 2 fault line, a heterogeneous permeability, and a randomly placed well location. So you see the well location is different for these 3 cases. And we use a type of mesh called Peppy mesh and applied refinement near our injection well. So if you look closely, each of these reservoir has different type of refinement according to the location of the injection well. And we apply these graph neural network architecture on this irregular mesh with the fault line, and we can get excellent performance of the prediction shown by this graph. So the top row is again simulation results. The second row is the surrogate model prediction, and the third row is the error comparing the ground truth with the prediction. And something that is really interesting about graph neural network based architecture is that it has a better ability to extrapolate onto unseen period. And we think that the extrapolation is coming from the fact that when learning things at a local scale, the model have actually seen more combination of different capillary, viscous, and gravity combinations within each local patches. So learning that on a smaller scale allows the model to generalize better into unseen period. So the model was only trained up to 400 days, but it generalized very well to 950 days. And the model also has excellent performance when it's generalizing into unseen meshes. This case shows 5 different unseen meshes, each have different injection, slightly different injection location, and the performance is consistently good across these. So that concludes our attempt with graph neural network. This paper was accepted very recently, so the citation is here. We encourage you to take a look if you're interested. And with that, I have introduced our journey from convolutional neural network to Fourier neural operator and to graph neural network, where we gradually add more complexity into machine learning modeling process. And I think we have found that there are enough evidence supporting our claim that there can be a general purpose numerical simulator alternative where the user can just directly use the machine learning instead of running the numerical simulation. And the numerical simulation can be run just one time beforehand for most cases out there. And the end user can enjoy the great computation acceleration coming from this approach. So thank you very much for listening. With that, I'll end here. Happy to take any questions.
Gege. So we have a question in the chat from Al Hassan. Thanks for the talk. What was the main criteria for splitting the training and validation sets?
So a general rule of thumb for general machine learning is to split the train and validation with a 8-to-2 or 9-to-1 split. But whether your the number of training data is enough is determined by your performance on the training and the validation set. So if your validation is a lot worse than training, that means you need more data, the total number of data, and you can still maintain the same split ratio, but increase your data sample until you have a similar train and testing performance.
But with your different networks, you've chosen different ways of splitting. So the graph neural net, you're choosing only the first like 100 time steps or whatever, and then extrapolating onto the next 200. Whereas the FNO, I think, and the CNN, you're looking as a validation the unseen data sets.
Yes. So for one thing that I haven't touched on a lot is that for FNO and CNN, we didn't treat time as time. We treat time as an additional dimension. So time is treated the same way as spatial, but just represented as an additional dimension. We were able to do that because we were able to fit that into the memory. If we can't fit that into the memory, people need to revert back to autoregressive. And when you do autoregressive, you can actually treat time as a different thing, and that way you can go to unseen period. Way before you have less error accumulation, but you can't really go forward in time.
So Alison, as a follow-up, is how you made sure that there's no leakage between the training and validation.
So I'll try to answer with my assumption on the question. So when I think about leakage from the training and the validation is, for example, if I have 2000 permeability map in total, and the 2000 permeability map is matched into different type of geological condition or injection scheme and split into the training and validation. So in your training, you have seen this 2000 different variation of permeability, and in your test, you're seeing the same variation of permeability maps again. That's when I see leakage, when you have these cross information between your training and test. But in our case, we sampled each dimension independently, so we never have any information in the test set that is being seen during the training. I hope that answers the question.
Probably. So I have a question. So when you're doing faults, do you think that same methodology would work for very small features such as fractures, where they're really, really sub-resolution?
Sub-resolution.
As in, like when you think of a fracture that's maybe a couple of like tens of centimeters long, but actually like only that thin. So you end up with assigning a permeability to a cell that's quite large, but most of that permeability is coming from a very small resolution feature.
I see. So machine learning today, the best it can do is still just replicating what the data provides. So whatever the fracture, however the fracture is treated in the training set, the model will be able to replicate the same effect. But if it's not treated properly in the training data set, then there's no way the model can learn it.
Okay. Thank you. Gege, do you have any questions?
Yeah, I can add a general question. So how does this type of approach compare to like traditional reduced order modeling approach?
These type of models can generally be a lot more powerful than traditional ROM-based approach. There are studies out there that compares the performance. I haven't personally done it, but you can see these really high-dimensional permeability maps. Those are typically very difficult for ROMs. Yes, so I think this gives us a lot more predictability.
Thank you.
So I have a sort of a theoretical question. So what do you think is the most important thing that's missing from your model? What's next?
My read on this type of technology is that it is almost ready for these type of technology to be moved into industry. I think the research is pretty mature. There are lots of different people, different groups out there developing different architectures, and we think together, the scientists in this domain in the past 5 years has proved the fact that these models can predict good predictions, and the industry is taking this into their simulators, replacing small or big parts of their existing simulator. So that is one hand. On the other hand is there hasn't been a lot of study on the robustness part of these models, and that is a direction that I personally find very interesting. It's similar to how large language model is framed these days. How do we confine these models and make these models report when you think that there's a high chance that this answer is not correct? That requires some further development.
We have a question from Marcos. Have you considered embedding physics information into any of the neural networks you showed? Do you think that any of them could benefit from this feature?
Yeah, that's a great question. And there are a lot of people explore models on this direction. I think for CO2 storage, where we have a very sharp interface, a very discontinuous shock front, it is hard to embed the physical information, because anytime we're introducing very high degree of discontinuity into the model, it makes the training very hard, and the loss manifold is no longer nice and smooth. The model can very easily explode when we introduce these type of physical loss. So that's my experience. Haven't seen much success in this direction for large scale 2D CO2 storage yet. But it is a very active domain of research.
So I guess I sort of maybe I misunderstood with this question, but so when you have your multi-level approach, when you get down to the finest level, the coarsest level, does the size of that make prediction of extreme cases where you're having a very fast plume migration more difficult, just because it's outside of the it moves faster than a single mesh block would move? How does that affect?
The size of the smallest LGR, does it affect how the prediction accuracy is?
It's sort of going towards your earlier statement about how it would affect the model in more extreme cases where you're having more like faster movement of plume migration. Maybe this is a stupid question, I'm not sure.
So maybe I can try to answer from how we design the data set. So if there are cases where we have very fast front movement, we try to put that very rapidly changing phase in our finest. So the finest grid resolution is already considered all of the combination that we can think of, where you have really quick pressure buildup and very fast front movement. And the grid that you see have already incorporated that effect after we do the grid analysis study. So we get that from the sensitivity analysis.
Okay. I think I'll have to read the paper. All right. Well, thank you, Gege. I think we're out of questions unless Mingjia, do you have any further?
No, I think it's all right. Yeah.
Okay. Well, thanks. So with that, we're excited to announce our next session, which will take place on the 12th of November at 2 p.m. So in this session, we'll host two early career researchers, Dr. Andre Debrabson from the University of Birmingham, who will present assessing the resilience of offshore wind farms against climate change through monitoring of soil structure interaction, and Dr. Craig Bauer from the University of Leicester, who will present his work on self-learning digital twins for sustainable land management projects. Additionally, on behalf of UKRI and the AI for Net Zero program, we'd like to highlight a conference that we're hosting, which is taking place from the 16th to 19th of December, 2024. The University of Exeter will host the 4-day event, bringing together leading experts and high-profile speakers to discuss how AI can drive meaningful progress towards achieving net zero. So registration is now open, and you can find more information through the link in the chat. So with that, I will conclude, and thanks again to Gege and my co-convener, Mingjia.
Thank you. It's my pleasure to be here. Okay.